My name is Evan Sultanik. I'm a computer security researcher at Trail of Bits, and today I'm going to be delivering to you a sermon on the indulgences of computational sacrifice, or alternatively, the superabundant benedictions of programming an absurd NES game. So, who am I? If you're really interested in the details, you can take a look at my resume on my website. And much like dairy products, you should always check the date in the corner before consuming the content. And as you can see, this is the resume that I submitted to Trail of Bits when I was applying for a job a few years ago. Now, the reason why I'm showing you this specific version is you might notice at the bottom there are some curious footnotes here. First, it's asking you to unzip the PDF of my resume, and you'll get something related to Git. It also says that it's a Nintendo Entertainment System ROM. Also, somehow the footnote here is printing out the MD5 sum of the PDF itself, and so on and so forth. So let's confirm some of these things. Sure enough, the MD5 sum that was in the PDF is correct. And also we can unzip the PDF and we get another PDF inside that has something to do with Git. File doesn't think it is a PDF or a zip, it thinks it's an NES ROM, so let's try emulating it. Sure enough, the NES ROM prints out the same MD5 sum. You can download this PDF on my website, as well as emulate it directly in your browser using an Emscripten compiled version of the NES emulator FCEUX. I apologize for my really poor gameplay. I recorded this really late at night. So I don't want to spoil all of the Easter eggs and gameplay of this. You can go and try it yourself. But in the remainder of this talk, I'm going to be talking about some of the technical challenges in creating this, and also how that can be applied to real work. So why is this resume different than all other resumes? Well, it's not because I'm looking for a job. This is a hobby. It's really fun to do these types of things. And it's really fun to program in a constrained environment. So for the remainder of this talk, I'm going to be giving you examples of how those constraints can teach you to be creative and learn things and techniques that you can actually extend to modern software. In order to do that first, we have to go back to Pocker GTFO. I am a frequent contributor to and an editor of Pocker GTFO. I've been involved with the publication for a number of years, however, not since its original inception. It is a roughly quarterly journal that is always released for free. You can see my mirror here, but we encourage you to make your own mirrors. There is no official website. We always release on paper first at a conference, when conferences, of course, are held in person. And then shortly thereafter, we release a digital version, and the digital version is always a polyglot of some sort. It's a PDF, always typically a zip, and something else. Ruby scripts, Flash, tarballs, JPEGs, all sorts of things that you wouldn't expect to be able to be a valid PDF at the same time that they are. I should mention here, POC stands for proof of concept, or alternatively, pictures of cats. I say this because other meanings of POC have become increasingly popular since this publication was originally named. So if you're reading this in public, particularly, and the laity doesn't necessarily understand that the double bar means or, so you can get some weird looks. Also, one of the most common questions we are asked is why, well, it appears as if you're numbering the issues in hexadecimal, but you skipped over A through F. You went straight from 9 to 10. Why is that? Well, it's because we number in binary coded decimal as a tribute to the floating point unit of the HP Saturn architecture. We also have a number of publications you can purchase. They are published through No Starch, and in fact, we just released a third volume just recently. They are chronological collections of the articles that we have published. This is published at significant expense to all of the editors, and we don't make any money off of this. It wouldn't be fair to either us or the authors. So all of the proceeds go to funding those free print runs, and whatever is left over is donated to charity. So I encourage you, please purchase a copy of our faux leather-bound, gilded-edged books at any purveyor of fine books, or Amazon if you need to. But I highly encourage you to buy directly from the publisher, No Starch. So if you have a copy, please rise and open your hymnal to chapter 7, verse 6 for a recitation of some fine words by Angel Albertini. A file has no intrinsic meaning. The meaning of a file, its type, its validity, and its contents can be different for each parser or interpreter. So why do I bring up Pocker GTFO? Before I created this crazy resume, in issue 14 of Pocker GTFO, I got interested in creating a PDF NES polyglot. And this technique that I'm going to be talking to you about for creating this polyglot had been known for some time. It was independently discovered by Angel Albertini and Evan Turan. But I wanted to create, I thought it'd be cool to create a custom NES game, well, game in quotes, a ROM that when you ran it, it would represent or recreate the title page and the table of contents for the issue. So in order to understand how all of this works, let's talk about the NES architecture. In the Nintendo Entertainment System itself, you have a CPU, a separate audio processing unit, and a separate picture processing unit. Inside the cartridge, there are typically at least two chips. There's the PRG ROM, which contains the program code, but then the sprites and graphics are stored separately in the CHR ROM. That's because the PPU only talks directly to the CHR. There's typically no way for the CPU or your actual program to draw directly to the screen. You have to use pre-encoded sprites in the CHR. That's typically read-only memory. Sometimes cartridges could have RAM, where then your program could actually write into the CHR and change the sprites on the fly. And there's also a mapper chip, which can actually do paging. Remember, this is an 8-bit system. You can't address that much memory. So what did games do if they needed more space? Well, the NES in the early 80s had memory paging before it was available in Intel processors, which is kind of crazy. So what the mapper does is you can write to a special address in memory. The mapper will intercept that and then page out different regions of PRG ROM or CHR ROM or RAM. But you could have any custom circuitry you wanted in the cartridge, as long as the CHR and the PRG worked as the NES expected. So this is why emulating cartridge-based systems, and in particular the NES, is so difficult. And that's because there were dozens of different mappers that came out for different games. Some of them were bespoke to individual games. So in order to write an emulator for the NES, you need to implement support for the logic in every single one of those mapper chips. This is actually how the Game Genie works too. So the Game Genie is basically its own mapper chip that intercepts all of the communication between the NES and the cartridge, and can twiddle some of those bits if necessary. So given the fact that there isn't a single contiguous region of memory for an NES cartridge, right? It's split up between various banks of PRG ROM and various banks of CHR ROM or RAM. We need to have some file format to represent this. You can't just dump an NES cartridge to a single file. You have to have some sort of header to say what type of mapper is used, if any, and how many banks of PRG ROM, how many banks of CHR ROM or RAM there are. So nearly all emulators these days use a format called INES. So this is the format, relatively simple. There's some magic. You specify how much PRG ROM there is, how much CHR ROM there is. There's some flags, and so on and so forth. But there's also this optional trainer section toward the beginning of the file. And what this was used for was way back when, before emulators had support for all of the mappers, it was often necessary for a ROM where the person dumping the ROM knew that there wasn't mapper support yet. They could add custom code in the trainer section that would be patched into the PRG ROM to implement whatever functionality of the mapper was necessary. So this was kind of a hack to patch ROMs or hotfix ROMs so they could be emulated without necessarily having emulator support for the custom hardware in the cartridge. Okay, but these days, trainers are almost not ever used in NES ROMs. Okay, so let's now look at PDF. So, because remember, we're trying to create a PDF that's also an NES ROM. I have another talk that goes into a lot more details on the PDF file format and why it is so broken in many ways. That was given at Empire Hacking almost exactly a year ago, on December of 2019, I believe. It's on YouTube, so I encourage you to check that out. But the part that will be relevant here is that PDF typically just don't care. You can have two PDFs, and a PDF reader or interpreter or renderer will almost always ignore everything before the PDF header. The PDF header does not need to start at byte offset 0. Also, there can be junk trailing after the end of the PDF. So the PDF does not have to end at the PDF interpreter will ignore everything that happens after the trailer of the PDF. So one fun thing to play around with is take two different PDFs and just concatenate one after the other. Load it in one PDF renderer, and it might display the first one. Load it in another PDF renderer, it might display the second one, but almost no PDF readers will give you a complaint. So the thing to understand here is that or the lesson from this is that under-constrained format specifications lead to what's called file format schizophrenia, or parser schizophrenia. That's where a single file is rendered differently by different implementations of the file format. So we're going to exploit this to create our NES PDF polyglot. So we have our NES ROM, we have our NES header that we talked about, and here we are going to enable that 512-byte trailer. Inside of the trailer, we're just initially going to fill it with zeros because it's not actually used for anything in emulation these days. But that gives us space to put our PDF header. And remember, PDF doesn't care, for the most part, about junk that happens before the PDF header. So we'll just ignore the INES header. Then immediately, we can create a PDF object, and PDF objects can contain arbitrary binary blobs. So we create a PDF stream object that has a length of the number of bytes remaining in the NES ROM. So we encapsulate the remainder of the NES ROM in that stream object, we end the stream, and then we include the remainder of the PDF. That's it. That's how we did it for Pocket GTFO issue 0x14. As you can see, it will actually run on real Nintendo hardware. And it's rendering the table of contents for that issue. And you can see that it's also printing out the MD5 sum of the entire file, not just the NES ROM part. So this is the same MD5 sum that is printed in the PDF. So if you think about this, the naive way to do this sort of MD5 quine would be to write a program that is able to read all of the bytes of itself and then calculate the MD5 and print it to the screen. But we couldn't possibly be doing that in this NES ROM because it doesn't have visibility into any of the bytes inside the PDF, which affect the MD5. So how are we doing this? It's a little bit trickier. How does that work? You can see we also did this in the in my resume. Well, if you take nothing else away from this talk, I hope that you realize that MD5 is dead and has been dead, and you shouldn't use MD5. Hopefully you already know this. Dr. Mark Stevens of Microsoft Research has done a lot of seminal work in breaking MD5 and showing that it's no longer a viable hash function with today's computational speed. So he released a number of tools in the HashClash project, one of which is called fastcall. So what you can take is a file or a prefix to a file. You can submit the file to fastcall, and it will emit two 128-byte suffixes that have a few interesting properties. So the first property is that if you append each of those suffixes to that prefix that you initially submitted to fastcall, they will have the same MD5 sum. But those two suffixes, A and B, are actually different. If you take a look, they differ by 1 byte. And in fact, it's even more subtle than that. It's not just 1 byte. If you look at those bytes, they only differ by their most significant bit. And this is actually guaranteed by fastcall. The most significant bit of the 60th byte is guaranteed to differ. So we can use this to encode the resulting MD5 sum without actually changing the MD5 sum of the file. So here's how we do that. We take a file, we find a good place inside of it to put this encoding. It's going to be, there are 128 bits in an MD5 sum, 128 bytes per collision, so we need 128 times 128 bytes to actually store this encoding. We split the file in half, and then we iteratively run those 128 collisions, one after the other, insert them in the file. Then, we can put whatever suffix we want after that, actually. Then, later on, when we're done with the file, we calculate the final MD5 sum. We see all of the bits of it, and then we can choose the resulting either A or B pairs to encode whether each bit was 1 or 0. Then we can use, in the case of the NES ROM, we can programmatically read over those, look at the most significant bit of the 60th byte of each of those collisions, and be able to reconstruct the MD5 sum. It's a little bit more difficult for the PDF version. You have to do some tricks with JPEG, but it's also basically uses the same technique. But that was 128 bytes times 128 times. And actually, if you were to do it naively to encode that, it would take around 32K to store just the MD5 collisions. To give you some context, that's more than the entire ROMs, the entire games for Donkey Kong and Duck Hunt. So how can you store all of that data? Well, it turns out with some clever encoding, you can cut that a number of bytes in half. But still, that's a huge chunk of space in an NES ROM, and it requires. It didn't require using a mapper for the Packer GTFO issue, but with all of the other ambitious stuff I wanted to do with my resume, it did require switching to using a mapper and doing some paging. So let's go back to the resume. So here's one of the things I wanted to be able to do. If you take my resume and you run this command, which is basically just looking at the 40 bytes starting at byte offset 0x1337, then you get this cute Easter egg. Now I have a number of hints in the game that I won't spoil for you for how to discover this, but this is what I wanted to be able to do. But that meant that I needed to have those raw bytes to exist at that specific offset within the outer PDF file. So in order to do that, I needed to play some tricks with the cartridge hardware. Specifically, I needed to use a mapper. Now, the first mapper I tried was the easiest one for me to use. However, it only had the option to swap out the entire PRG ROM at one time. But that presents a problem. The PRG ROM contains the code that we're currently executing. If that code calls into the mapper to swap out a different PRG ROM, the immediate next instruction is going to be from the bank that we're swapping in. So then you need to do all sorts of alignment tricks to make sure that the code in the bank you're swapping in is aligned with the code that you're calling from, and it's a huge pain. So I used a little bit of a hack to get around that, so I didn't have to make sure all of my code was aligned properly between PRG ROM banks. What I did was I created a little piece of trampoline code that I could copy into RAM. Then I would jump into RAM, jump into that trampoline. The trampoline would be the code that calls the mapper. It would swap out to PRG ROM bank 2, and then jump back into the code in PRG ROM bank 2. So the lesson here is that not all memory is created equal. but memory is memory is memory. Nothing prevents you in the NES from just copying code almost anywhere that the CPU can address and running it from there. The next trick I wanted to be able to do was implement a Brainfoo interpreter that implemented a quine. So this is Brainfoo code that prints out a copy of itself. And in fact, Evan's Sultanik quine guard is necessary for it to be a quine. If you change any of that code, it will not work. So this was inspired by a project by Vi Gray. He actually, I'm not sure if it's still in production or for sale, but he had these amazing NES cartridges with his Brainfoo interpreter that you could run on real NES hardware. The issue was it had a limit of 1024 instructions, and that was mostly limited not by the ROM inside the cartridge, but actually by the RAM of the NES. It takes a lot of RAM to emulate this sort of thing. I believe he has since improved the memory efficiency and been able to double that number of instructions. But even so, my quine would have easily surpassed the RAM limit, especially given all of the other RAM I was using for everything else in my game. Moreover, my quine was so large that it would require almost one ROM bank just to store it. So how could we fit all of that inside? How did I make it work? Well, the first observation is that there are a finite number of loops in the quine. Second observation is that some loops only ever iterate once, or a finite number of times. And the last observation is that some loops are what I call monotone. They always iterate at least as many times as the last time that loop was entered. So what that allows us to do is, outside in a Python script, record an execution trace of this Brainfoo quine and record how many times each loop executes. Then we can record which loops execute a constant number of times, which loops are monotone, and then for the monotone loops, we only need to store deltas, right? So if a delta in terms of how many more times the loop will execute given the last number of times it executed. This uses lots and lots of cheap ROM. It's cheap because now we can page it in and out using our mapper. And the only RAM it requires is less than 20 bytes. So like orders of magnitude decrease in RAM usage. So the lesson here is that not all trade-offs are between space and time, and not all space is created equal. So if I've inspired you a little bit to get into NES development or any type of like retro console development, this resource didn't exist when I started, but it's amazing and a great way to play around with things and get started. I encourage you to go to 8bitworkshop.com. They have a web-based IDE where you can program both in assembly and in C, and I believe also some other languages for a number of different retro architectures, including the Nintendo Entertainment System. They have a bunch of sample code, and it's a great way to get into programming in these constrained environments. The one tip I'll give you is that even if you are super familiar with assembly, I wouldn't jump in directly to assembly programming. I would start with C. And actually, if it is feasible on the architecture you're interested in, I would even start with BASIC. Okay, now you might balk with that because if you've ever programmed in BASIC, or if you open up a BASIC textbook, the first thing that you're going to see in chapter 1 is, line 10, print hello world. This is so grotesque, right? Like, ugh. But if you skip ahead to chapter 6 in almost any BASIC book, you're going to see something like this. So think for a minute about the educational density of these few lines in the book. It's asking the kids to peek into the brain, the operating system of the computer, and poke some bytes, right? Think about how much that is teaching you about how these systems work, how, for example, the CPU interacts with the picture processing unit and the audio processing unit. And you can do it all in a language with very little in the way of an initial learning curve, and with a lot of safety built in. So if I've offended you by this opinion, this hot take, which I hope I have, I encourage you to read more about it in Pastor Manuel Lefroyg's sermon concerning the divinity of languages in Pocket GTFO issue 2, chapter 7. There is a very famous Soviet film called Ironia судьбы или с легким паром. And it pokes fun at Brezhnev-era public housing and architecture. And what happens is the protagonist gets pissed drunk, as one does in the airport, and mistakenly gets on the wrong airplane. He thinks he's going back to his home town of Moscow, but instead he lands in St. Petersburg or some such. He gets out of the airplane. He doesn't notice it's a different city. He goes to a taxi. He gives the taxi driver his address. And then the taxi arrives in an apartment building that looks identical to his home apartment building. He goes to his apartment number, which the door looks identical to his home. And sure enough, his key works in the same door. And all of the furniture looks very similar to his own furniture, so he crashes for the night. When he wakes up, your favorite romantic comedy ensues. So I'm going to convince you that the Soviet Union is Microsoft, Brezhnev is Windows, the apartment building is kernel 32.dll, and the protagonist is malware. So let's look at the anatomy of a Metasploit exec payload. Right, so malware payloads are typically constrained in many of the same ways that our NES programs are constrained. Right, they can't be over a certain size to fit within certain limits of the particular vulnerability that they're exploiting, and also they don't necessarily want to have certain signatures, so they don't want to have certain strings inside. So malware will almost always use a hash to hash the strings for various things that it's looking for. And in the Metasploit exec payload, it needs to find certain DLLs in Windows when it starts executing. So it needs to walk through the linked lists in the Windows kernel to figure out which library is which based upon their name. But they don't just want to store the string kernel32.dll in their payload. That would be a dead giveaway. So they need to hash the that string. And the way Metasploit does it is by rotating every byte into a sum. And by the way, this is joint work with my colleague Mike Myers that was published in Pocket GTFO issue 13, chapter 7. So the reason why it's using this rotation hash is it is super succinct to implement in x86. It just takes 2 instructions, right? So it's super compact, doesn't use a lot of space, but it works. It seemingly works pretty well as a hash. Well, it turns out that these types of non-cryptographically secure hashes are super easy to collide. You can do it with an SMT solver. It's almost instantaneous, right? So what you can do is you can create another string, in this case, a prefix to the string, that when you apply Metasploit's hash, they both hash to exactly the same thing. So the moral of the story here is that some constraints cannot be overcome. Sometimes if you need to have a cryptographically secure hash, you're going to need more than 2 instructions to work with. So what can we do with this? Well, we can modify the in-mem order module list in Windows and add our own DLLs that we have named to collide with kernel 32 according to Metasploit's hash function. So when a Metasploit payload is executed on our system, instead of finding kernel32.dll, it will collide with our honeypot DLL that we have included earlier in the linked list. So finally, I want to talk about Polytracker, which is an instrumentation tool that we've created at Trail of Bits. And specifically, I want to talk about how some of the lessons that we've learned in programming in our constrained Nintendo environment can be translated to this. So the problem that Polytracker and its associated tool framework are trying to solve is a given PDF, as we've seen already, can exhibit schizophrenia, right? So you could send it to a bunch of different PDF implementations, and each may behave differently. Adobe might crash, Poplar might reject the file as being malformed, MooPDF might just accept the file and render it. And it may actually contain an exploit that exploits a vulnerability in Foxit. So each implementation is interpreting the file slightly differently due to ambiguities, perhaps in the file format specification or the way the decisions they make about certain ambiguities in the file. So what we want to be able to do is automatically inspect both the file format and all of the extant implementations to automatically generate a subset of the file format that is likely to be safe across all implementations. So one of the ways that we do that is with Polytracker. So what Polytracker can do is it can take any piece of software, doesn't have to be a parser, but it will automatically add instrumentation to do what's called universal taint tracking. So we can run one of our instrumented binaries or an instrumented parser, and the Polytracker instrumentation will keep track of which byte offsets in the input file correspond to which functions in the parser. In other words, what parts of the input file each of the different pieces of the code are specialized in operating on. So for example, we can see that the ensure solid xref function corresponds to operating on the trailer and xref sections of the PDF. The format object function is operating on PDF object dictionaries, so on and so forth. The way Polytracker stores this taint information at runtime is using a forest data structure. So if we have this source code that Polytracker would be instrumenting, there would be a runtime taint forest corresponding to a root node for every input byte offset in the input file. And then when we read foo and bar, they would each get their own taint node corresponding to those byte offsets. Now I'm simplifying a number of things here, but then if we were to assign baz to foo and bar, the taint from foo and bar is being unioned together. So baz is tainted by both byte offset 0 and byte offset 1. So we add a new node to the taint forest for baz. Now, of course, there are a number of optimizations where we don't always have to create new nodes, but still, over time, this taint forest becomes huge. And it can take a lot of RAM, and it also takes a lot of I/O to store, and then it also takes a lot of CPU to process, to do all of our analytics and post-processing on. So how can we make this more efficient? Well, one of the things that we can do is implicitly index nodes based off of their location in memory, right? We don't need to store pointers between each of the nodes if we can just store an index of where those nodes are in memory if they are all in contiguous memory space. This saves over 16 bytes per node in our data structure, and which is a significant savings when you're talking about this size of a data structure. But the thing to note here is this is similar to our solution for storing the Brainfoo quine. So I hope that this has inspired you to try constraining your programming. Memory is memory is memory. Trade-offs always exist, but are not immediately apparent. And if nothing else, there is divinity in all programming languages. Thank you for your time. And here's how to contact me. And you can go to sultanik.com/NES résumé if you'd like to try emulating it yourself. Okay, so this is live Evan talking over this. There's about a minute of credits here. A few other people I want to shout out to that aren't in the credits, I don't think. Carson Harmon, who's my collaborator on Polytracker. Also Sergey Bradis, who funded a lot of this work at DARPA. I'd like to thank all of the Absolute AppSec people and the organizers of this conference. Logi for wrangling me to do this, and probably lots of other people that I'm forgetting. But I can field any questions you might have.
The sound, I'm waiting. I'm waiting for the sound. Oh, that's awesome. That was such a guy. That was an awesome talk, was it not?
Yeah, it was a great talk.
Thank you.
The way that started just from the very beginning was amazing, and then just continued. It was super fascinating. Didn't see the direction it was coming. That was really fun. We're asking if anyone has any
I need to go play Zelda now, I think.
Yeah, there are lots of Zelda Easter eggs. And by the way, if anybody has played Mario Maker 2, there's a DLC that actually has a Link character that has like Mario physics, and I was really upset because like that was released right as I was releasing my own version of that. And so yeah, Nintendo scooped me. Mario physics are really weird, by the way, too. The Mario 1 physics are really odd and hard to implement.
Evan, I have to ask this question because I know that Langsec is controversial, but like with all the work that you do with parsers and things like that, would you consider this a Langsec talk? Because I think that's the question that everyone was brimming with, and everyone is like 2 or 3 people who know what I'm talking about.
I will answer that diplomatically, in that I think that the talk stands on its own as obscure some obscure Nintendo development, but yeah, I'll leave it at that, I think.
No, everything is amazing. I love the work that you do always, with all the weird machines that you find, and it's absolutely a great thing. Weird machines is also a term as well for folks who are looking for things. But Evan does amazing work, but his PDF work and his NES work is always the most entertaining, I would say. So. But now, Evan, thank you very much for that.
Thank you for having me. It was really fun putting this together, or having a reason to actually make this slide deck. So, yeah.
I'm glad that we could have you, and I'm also glad to be the person after you, because now my talk can suck as much as possible, and no one will notice because I just came after that talk, and it's perfectly fine.
Yeah, Evan,
it'll be fine.
Yeah, you'll be fine.
Oh,
but yeah, we really do appreciate it.
Like, it's just that was an amazing talk, and I really do enjoy everything that you did there, Evan. Thank you very much for that. Especially with
thank you.
Well, good. I don't think we have any other comments for Evan or questions.
Everyone's just busy Googling. It's going to be 2 hours of Googling between Evan and Logi here, right? As far as making sure we understand what's up, right? Or at least attempt to have a question. That's where I'm at right now.
My talk is not nearly as cool as Evan. So there's no sound. It's mostly me ranting.
No worries. All right. Well, yeah, if there's no other questions for Evan, again, we appreciate it. We'll go ahead and let you off the hook. But for now, anyway, we'll be in touch. Thanks again, and thanks for inspiring us on this one.
Yeah, my pleasure. Thanks a lot.